Humans transition from walking to running at about 2 meters per second. That's the speed at which running becomes more energetically economical. Now, the majority of metabolic cost is consumed by muscles, so we might expect some muscles to become more efficient when we transition from a fast walk to a slow run. And muscle-driven simulations of walking and running reveal a possible mechanism. We can see that here. What I'm plotting is the force-velocity relationship. So here's the force-velocity multiplier versus normalized fiber velocity. And as you walk faster and faster and faster, here's a slow walk, and as you walk faster and faster, here I am walking at 1.75 meters per second. The fibers in your muscles are shortening quite quickly, so you're paying a penalty for that shortening velocity. Now, when you break into a run, a slow run at 2 meters per second, the muscle fibers actually slow down in the gastrocnemius, so they generate more force for a given level of activation. The same is true for the other big plantar flexor. Walking at 1.75 meters per second results in a significant shortening velocity. When you transition to a slow run, the velocity goes to 0. Because the tendon is compliant and forces are higher in running, the tendon is stretching more and the muscle fibers go slower. So it's somewhat counterintuitive that this transition from a fast walk to a run actually slows the muscle fibers. Dom Harris and Greg Sawicki noticed this in some ultrasound measurements of the gastrocnemius, and that motivated us to build a muscle-driven simulation to explore this more deeply. And indeed, we found the same thing that they did. So muscles activate more highly when you run faster. And I'm showing just this picture from the book. It's the activation patterns of 11 muscles. And there's really two things that I want you to notice. One is that as you run faster, it's basically just scaled up versions of the muscle activations. So if you look at gluteus medius, for example, the light colors are the slow runs, the bright red are the faster runs, and you see it's just a scaled up version. Same with rectus femoris here. The activations are just increasing. Same with vasti, activations just increase. But what I also want you to notice is the other thing is the running activations are dramatically different from the walking activations. If you look, for example, at the soleus here, you see just here's walking shown in blue, and the running and running speed shown in red. It's just fundamentally different activation patterns. Same is true for the gastroc medialis and gastroc lateralis. So some of the muscles undergo a fundamental shift from walking to running, and then once you're running, at least at these relatively low speeds, 2, 3, 4, 5, even 6 meters per second, the activations just scale up with speed. So at these lower speeds, 2, 3, 4, 5 meters per second, you notice that you get longer strides at higher running speeds. So you can see that here. Here's a muscle-driven simulation at 2, 3, 4, and 5 meters per second. Those longer strides are enabled by higher ground reaction forces. So what I'm plotting here is the ground reaction force in body weight versus the percent stance, where the low speed is here, 2 meters per second, 3, 4, 5. Sorry, I don't have the axes here, but that's why I'm pointing them out. And these greater ground reaction force produce a longer flight phase and a longer stride length. Now that same thing holds true up to about 7 meters per second. So what I'm plotting here is on one axis the stride length in meters versus speed. And what you can see at these low speeds, stride length is increasing pretty dramatically, up to about 7 meters per second. And those increases in stride length are made possible by greater ground reaction forces. Stride frequency is relatively constant. Remember that kangaroos, when they were hopping, their stride frequency was relatively constant at their resonant frequency. The same is true at running, especially at these low speeds. As we start to increase speed a little more, stride frequency is increasing, but not as much as stride length is. Now, when we get to 7 meters per second, stride length no longer increases. Why does that occur? It occurs because at those high running speeds, your ankle plantar flexors have to contract very rapidly, so rapidly that the force velocity effect is limiting the muscle's capacity to generate force. So above 7 meters per second, it's very hard to get longer stride lengths. The only way to run faster then is to increase the stride frequency, and you see that happening here. Well, how can stride frequency increase? Well, remember the rectus femoris and hamstrings? So these are the muscles that swing the legs very rapidly. So rectus femoris on the front, pulling it forward, hamstring pulling it back, together with the hip flexors, iliopsoas and G-max. Those sets of muscles at these very high speeds enable you to swing your legs very quickly. So the very highest running speeds are achieved by high ground reaction forces generated primarily by the ankle plantar flexors and vigorous switching of the legs, high speed sprinting enabled by the hamstrings and the rectus femoris. So that's the run to sprint transition. And I would make that transition at roughly 6 to 7 meters per second, depending on your leg length. So let me just review some of the key points for muscle-driven running. Number one, muscles generate essentially all the ground reaction force. We don't get any support out of the skeleton. Number two, muscle-driven simulations reveal which muscles are responsible for generating the vertical ground reaction force and propelling you forward. The transition from walking to running counterintuitively slows the muscle fibers. And finally, the transition from running to sprinting is enabled primarily by the muscles that enable your legs to swing faster, rectus femoris and the hamstrings. So that is the close of the formal part for Chapter 12. What I do want to do is just finish up with a simple story about how muscle-driven simulations can help you design a device that will increase running efficiency. So I'll come back in a minute with that.